Hello Calculus student, this video is for 5.3 part 2. So the fundamental theorem of calculus, the most important part in this chapter, which is always to calculate the definite integral AB f of x. Definite integral AB f of x. And we finally come to the conclusion that, if f of x is continuous over the closed interval, then the function f, which is any antiderivative of f of x, you can use. You can plug in the upper limit minus the lower limit will actually equal to the derivative to the definite integral. That means the area under the curve. So we are tying the two together. And when we evaluate fb minus f of a, the big antiderivative, fb minus f of a, we use this notation of f of x as straight line b a like that to denote fb minus f of a. Because in the past, when we have function notation, we have f of something, right? But this is not a function per se, it is an area under the curve. But we do want to substitute the antiderivative and of two numbers, the subtraction. So we do it this way. When I want to do fb minus f of a, we say f of x vertical slash a from a to b. Meaning, to calculate definite integral, now we use antiderivative at the endpoint. So we no longer need to do Riemann sum limit. We no longer need to do the geometric formula, like drawing a circle or drawing a graph like that. So it is really nice. So from now on, when you need to calculate area under the curve, or when you want to just calculate a definite integral, you will use this fundamental theorem of calculus part 2. This part is proved in, of course, it's depending on part 1 to prove, and it's proved in the textbook. So I don't want to spend time to do this. If you're interested, you can refer to the textbook. They have a lengthy discussion on how to do it. Maybe in the Zoom class, if I have time, I'll do it. But mostly not likely, unless I do have time, because in the summer, the class goes really quickly. So let's say I'm going to evaluate each of these. Example 1. So let's spend time to work on them. So I have the function 2x minus 1. So by now you would know, if someone gives you a notation like this, your mind should think of, I have a line 2x minus 1, right? Maybe I'll put it here. I have a line 2x minus 1, right, 2, 1, 2, right? And I want to find the area from negative 1 to 0. Whoa, negative 1. So negative 1 is here, so 0 is here. So it is actually, if you graph it, it's actually a negative area, right? So in the past, we'll say, well, we can find it with the trapezoid, or if I don't want to do trapezoid, I can do Riemann sum. Now we do f of b minus f of a. That means I'll find the antiderivative of 2x minus 1, and then I plug in b minus plug in a. So what's the antiderivative of 2x minus 1? The antiderivative of this would be 2x squared over 2, right? Because 2x is 2x to the 1, minus, if I have a constant, the antiderivative is x. And then I need to plug in what? From negative 1 to 0. That's how I write it. Do the antiderivative and then plug in ba. Now that means that is x squared minus x, right? That means 0 squared minus 0, subtract, so this is b, right? Subtract a, negative 1 squared minus 1, minus negative 1, minus negative 1. So in this case, it will be 1 plus 1, so that is minus negative 2. So it's agree with what we suspect. It is a negative area. Okay, so let's do the second one. The original function was 3x squared minus 1. That is the function that is you know, you think about it, it's like a parabola under this, and we want to find the area from 1. I think from 1 maybe outside, not here. From 1 to 2. Okay, we want to find this area. Now, of course, you cannot do geometric formula. The only way to do, if we do not use the fundamental theorem of calculus, is to use Riemann sum. But now we know the antiderivative, we can do it. So it'll be 3 times x to the 3 over 3 minus x, because 1's antiderivative is x. I plug in from 1 to 2. So that means I'm going to plug in. So this is equal to x cubed. Plug in 2. So 2 cubed minus 2 minus 1 cubed minus 1. So that would be 8 minus 2 is 6. 1 minus 1, this is 0. So that's equal to 6. So this area is 6. Or this definite integral is 6. Do one more. So I want to find area under the curve from 1 to 9. So I always draw a picture to visualize it. So 1 to 9, I want to find this area. I know it's positive. It's actually quite big, right? So what would it be? I'm going to do f of b minus f of a, but the antiderivative. What is x? X square root x is x 1/2. So I'm going to use power rule to do the antiderivative. So it'll be x to the 1/2 plus 1 over 1/2 plus 1, right? Plug in 1 from 1 to 9. So so that would be x to the 3 over 2 times, so 1/2 plus 1 is 3 over 2. So the 2's go to the top, the 3 stay in the bottom, right? 2, 2, 3. So 1, 9. Now I'm going to plug in 9 first. Will be 2 over 3, 9 to the 3 over 2 minus 2 over 3. We only have one term in the whole thing. 1 times 1 to the power 3 over 2. So 2 over 3 to the power 3 over 2 is square root of 9 and then cube. So it's 27, right? 2 times 27. 2 over 3 times 27 minus 2 over 3 times 1, right? So 2 over 3 times 27, this is, well, we'll just keep the 3. So this is 54 over 3 minus 2 over 3. So that is 52 over 3. Is it a good number? We'll just leave it that way. We'll leave it as a fraction, 52 over 3. I have a question that you can try in class. And then the next one is a trig function. 0, area of sine, which is like that, right? But from 0 to pi over 4. I want to find this area. So, of course, this is not available in even Riemann sum. So the only way you can do it now is with the antiderivative method, fundamental theorem of calculus part 2. So I do the antiderivative of sine theta. What is it? It's negative cosine theta. And I need to plug in from 0 to pi over 4, right? So so that's it. So negative cosine pi over 4 minus, so this is a minus, so just keep track of the sign, minus cosine 0. Negative cosine pi over 4 will be negative root 2 over 2. Minus minus is plus. Cosine 0 is 1, so that is 1 minus root 2 over 2. For exact value, you just leave it that way. Okay, so any more? Oh, 2 more. So this is doing an integral from 0 to pi over 4. Secant theta, tangent theta. Do you remember what the antiderivative of secant theta, tangent theta is? It is secant theta. So the antiderivative is secant theta. And then I have to plug in the interval from 0 to pi over 4. So that means that is secant pi over 4 minus secant 0. So secant pi over 4 is 1 over cosine pi over 4. That is 2 over root 2 because the original one is root 2 over 2, so it's 2 over root 2. Minus, what is secant 0? So it's 1 over cosine 0. Cosine 0 is 1, minus 1. So this is the answer. So the number 6 is a little tricky. We have the function being an absolute value function. So what is the absolute value function? Absolute functions is, you can write it as x, if x is greater than 0 or equal to 0, is negative x when x is less than 0. So I'm just going to rewrite it this way. But when is x equal to greater than 0? When is it less than 0? So my interval is from negative 2 to 3. So I'll write it as maybe from negative 2 to 0 first. All these, I'm going to write negative x dx. And then I'm going to do 0 to 3. So these two are identical, right? Due to definite integral properties. And then, but because they're positives, so I will just x dx. And then when I do the derivative, I will have negative x squared over 2 from negative 2 to 0 plus also x squared. Well, actually just x squared, but not negative. 0, 3. So now the first one, you have to do f of 0 squared over 2 minus negative of negative 2 square over 2. So it's really convoluted. So it is become plus or plus, right? 4 over 2, that's become 2. Now I add, this has two numbers, would be the 3 minus 8. So 9 over 2 minus 0. So plus 9 over 2. So change into common denominator, 13 over 4. So that's very easy to do definite integral. Do you agree? So that is how we do 5.3. So that's the most important part of from 5.1 to 5.3. So all in all, we can summarize it as, so the next one is 5.4, which is use of the this integral to solve some work problem, primary work problem, and also work on some more difficult integration or definite integral or indefinite integral. So that is 5.3.